Let's work out a couple of example problems. Here's one that's based on the human being. Man's arm pivots at the elbow joint. So if you look right here, it's labeled fulcrum because that really is the pivot point. It's 1.5 inches from the insertion point of his biceps. So from there to there, that distance is 1.5 inches. If the distance from his elbow to his hand, so that now this is the distance from here to there, is 12 inches, it says. How much force must his biceps exert to lift a 25-pound weight? So here's a 25-pound weight that's pulling down, and our question is, what's the force that the biceps have to exert to make this happen? Free body diagrams are very important for solving point force problems, and that's no different for torque problems. A free body diagram is a good place to start. I'm going to model this person's arm by just using a rectangle here. Here are some things that I know from the problem. I know that the pivot point, the elbow, is 1.5 inches away from the insertion point of the bicep. So that means I have this force up here, I'm going to call it FB for bicep, that I'm trying to find, that's 1.5 inches away from the pivot point. I also know that I've got at the hand a 25-pound weight of 25-pound force pushing down, and that distance there from the pivot point to the end of the arm is 12 inches. Well, I can solve this problem by making a torque balance. If this is going to lift, if this bicep is going to lift this weight, then that means it's got to at the very least, come up to having the net torque on the arm be 0. So that'll be my solving point. If I can figure out what the least force of the bicep is that could cause torque to balance, then anything bigger than that will cause it to lift the arm, or lift the weight. So here's what I'll do. I'm going to say the sum of all torques in the clockwise direction must equal the sum of all the torques in the counterclockwise direction. It's called the torque sum. In other words, what I'm saying is, this is just another way of saying that net torque would have to be 0 here. So the clockwise torques would be produced by only the weight. That's going to cause rotation in the clockwise direction. So that would be a 25-pound force times a 12-inch lever arm. That would be countered by the counterclockwise torques. Well, the counterclockwise torque producing force is the bicep force. It's going to make the arm go the other way. So that means force of bicep, which I don't know a number for yet, times the lever arm of 1.5 inches would have to be equal to the clockwise torque. Well, now I have a very easy problem to solve. I just divide both sides by 1.5, the inches cancel out, and I find that the force that the bicep would have to exert is 200 pounds to lift this weight. Here's a problem that involves a pulley. It says a pulley has a diameter of 15 centimeters. I'm going to draw this pulley. A pulley is really just a wheel that's driven by a belt. It has a diameter of 15 centimeters. So that's the diameter. I symbolize diameter this way, like engineers often do. 15 centimeters. That's the distance all the way across. That's diameter. And it's driven by a belt with a tension of 20 newtons. So that means there's a belt pulling on this thing, and the force of tension is 20 newtons on that belt. And so the question is, what's the torque on the pulley? Well, we know that torque is equal to force times lever arm. The lever arm is going to be half the diameter because the pivot point has to be the center of the pulley. Pulleys spin around their center like that. So that means the torque on this pulley is going to be 20 newtons times half the diameter. Diameter is 15, so that'd be 7.5 centimeters. And probably, if I wanted this to come out in some standard units, I wouldn't want to use Newton centimeters, so I could change this into meters. And if I did that, here's what I come up with. 20 newtons times 0.075 meters. And when I calculate that out, I get 1.5 Newton meters of torque. In the last problem, I just left things in the English system because I knew the inches were going to cancel out, and my answer came out in pounds. Of course, if I was asked for and answer in newtons. I'd have to do some converting. Well, here's a slightly more complicated problem because there are two pulleys. Pulley has a diameter of 10 centimeters. It holds a rope which is lifting a 500 kilogram box. So there's a tension there. This pulley is attached by a shaft to a second pulley, and that pulley has a diameter of 35 centimeters. The person lifting the box pulls on a second rope, and that goes around this pulley. So what's the force exerted by the person is the question. I'm going to attempt to represent this with a little sketch. I've got one pulley here that's got a diameter of 25 or 35 centimeters. So the diameter of this is 35 centimeters, and there's a person pulling on this. FP, I'll call that. And there's a shaft attached here at the center of this thing. That's the pivot point for this. And that shaft goes all the way over to another pulley that's smaller. So here's this other pulley attached to the same shaft, so that's a pivot point for that shaft. And this has got a diameter of 10 centimeters, and it's got the force of this box pulling down on it. Now, in a problem like this, the torque here on this shaft, on this pulley, and the torque on this pulley have got to be the same torque, because if they're different, then that means you're going to somewhere in here rupture this shaft. The shaft is going to break or twist. So the torque on the 10 centimeter pulley has to be equal to the torque on the 35 centimeter pulley. So we're going to make use of that to solve our problem here. Well, there's a torque balance here. The sum of all the torques counterclockwise has to be equal to the sum of all the clockwise torques. The counterclockwise torques here are the force of the box times the lever arm. Well, this is a 10 centimeter diameter pulley, so that means from here to here is going to be 5 centimeters. So force of the box times 5 centimeters has to be equal to clockwise torque. Well, the clockwise torque is that provided by the person over this lever arm. So if this is 35 centimeters, then that means it's a 17.5 centimeter radius, and that's our lever arm. So the force of the person times 17.5 centimeters is going to give us the torque in a clockwise direction. There's a torque balance. Now, I know the force of the box if I do a little calculating, because it tells me that the box weighs 500 kilograms. So force of the box is 500 kilograms times G. And G is 9.80 meters per square second. So when you calculate this out, here's what you get. You get 4,900 newtons. So plugging that in here and solving for force of the person means the force person is equal to 4,900 newtons times 5 centimeters of lever arm divided by 17.5 centimeters. And the result, after centimeters cancel out and you do your calculation, will be newtons, and it's 1,400 newtons. So this person gets a little bit of a mechanical advantage here by having a bigger pulley. Here's another example problem. It says one end of a uniform 5-meter beam is sitting on a block wall. The other is supported by a crane, and there's a 500 Newton girl balancing 3.2 meters from the block wall. The beam's mass is given as 160 kilograms, and we're supposed to figure out what is the force on the crane. Well, we can do this by creatively selecting a pivot point that's going to eliminate one of our unknowns, because there's two things we don't know. And I'll draw a free body diagram in another format so we can see which those are. I'm going to model this situation with a free body diagram. Here's my beam, and there's a wall on one end holding it up, so there's a force there, force of the wall. The other end is held up by a crane, so FC for crane. In the middle, because this is a uniform beam, is my center of gravity. So there is a force due to the weight of the object, F of G I'll call that, the weight of the beam. And then in addition to that, I had another force acting here, and that is the force of this girl. And the girl has got a 500 Newton weight, So 500 newtons are pushing down, and they're pushing down at 3.2 meters from the end. It's a 5-meter long beam, so that means the distance from here to here is 2.5 meters, as will be the distance from here to here. That will also be 2.5 meters. So that kind of sets up the situation. Well, if this thing is perfectly balanced, then the clockwise and counterclockwise torques have to be matched. There are two things I don't know. I can figure out the gravity because I know how much the thing weighs. But I don't know the force on the crane, and I don't know the force exerted by the wall. Two unknowns. So I can only solve this for one unknown if I have only one equation, and that's what torque balance would give me, is one equation. So by selecting the pivot point here, I'm going to pretend that it's going to pivot around that wall. I now have no contributing force to torque through this wall because the lever arm would be 0. So this ceases to be an unknown for the context of this particular problem. So here's what I'm going to do. Here's my torque balance. Here are the sum of all clockwise torques. The 500 Newton force is going to make it go clockwise. So that's 500 newtons. And it's acting at 3.2 meters from the pivot point. That's my lever arm. Plus, the weight of the beam itself is going to create a clockwise torque. Well, I've got to figure out what the weight of the beam is. So I'll do that offline here. 160 kilograms is its mass. And if I multiply that by G, 9.80 meters per second squared, I will get the weight of the beam. And that turns out to be 1,568 newtons. So I've got that force, 1,568 newtons, acting at 2.5 meters from the pivot point. When I do these calculations, add it all up, then I should have a match to the other torque. Well, the counterclockwise torque that's here, the only one there, is due to the force of the crane. So that sum of counterclockwise torques is equal to force of crane times the lever arm. Well, the pivot point is 5 meters away. That's the length of the beam. So I can set these two equal to each other. So 500 newtons times 3.2 meters plus 1,568 newtons times 2.5 meters has to be equal to the force exerted by the crane times 5 meters. And if I divide both sides by 5 meters, well, I'll have units of only newtons. So I'll add this all up. If I multiply these together and then add the two products, I'll have Newton meters divided by meters is just newtons. So the force of the crane is going to be 1,104 newtons. Here's a follow-up problem to that. It's the same beam, same wall, same crane, same girl, everything's the same, except for now the question is not what's the force on the crane, but what's the force on the block wall. We don't know what that is because we eliminated it by choosing the pivot point on the wall. Let's go back to our problem and figure this out now. If we return to the free body diagram that I drew, there are two solutions to this problem. One is we could take our pivot point and just move it down to the other end. We could do that. And then just repeat this whole clockwise, counterclockwise torque balance thing and then solve for the force on the wall. But there is even an easier solution, because the other thing that's happening is, in addition to this thing not pivoting, it's also not moving up and down. So that means the net force is balanced. So what I can do here is I can just balance my forces. I can say the sum of all up forces has to be equal to the sum of all the down forces. The up forces are the force on the wall, which I don't know, plus the force exerted by the crane, which I now know to be 1,104 newtons. The down forces are the two weights. Well, there was the girl that weighed 500 newtons, and then we also found out that the beam itself weighed 1,568 newtons. So we solved this very easily by just subtracting 1,104 newtons from both sides, and we find out that the force exerted by the wall must be 964 newtons.